Well, this session, I want to talk about a fascinating example extracted from a book titled Applied Bayesian Inference, the case of Federalist Paper. In this book, two authors present very interesting examples of using Bayesian inference to decide authorship of works. Right? And this book is the first modern systematic Bayesian inference involving heavy user computers. And the book was written by Frederick Mosteller, a prominent statistician based at Harvard, and another statistician based at University of Chicago, David L. Wallace. And the work was done in 1964. So let me give you a bit of background about Federalist Paper, right? Or papers. The Federalist Papers is a collection of papers written under the pseudonym Publius by Alexander Hamilton, James Madison, and John Jay. There are a total of 85 papers, and out of 85 papers, 51 have been identified as written by Hamilton, 14 by Madison, and 5 by John Jay. Okay? And of the remaining 15, because tally them, put them together, total only 70 papers, right, are identified with their corresponding authorship. Of the remaining 15, 12 are in dispute and 3 are joint works to a disputed extent. Okay? So here, let me just talk about a very simplified example taken out of book to illustrate how to apply Bayesian inference and simple Bayesian estimation. Okay, so let's assume also this adverb is used 4 times, only 4 times in a 2,000-word paper written either by Hamilton or by Madison. And let us assume the use of the word also follows a Poisson distribution, because that is a count, right? That is a count. Well, people say, well, why Poisson distribution? Well, here, of course, we can use more sophisticated probability distribution. For example, negative binomial distribution, and that is actually used in the book. But for the convenience of discussion and presentation here, I only use Poisson distribution, and this is also a discussion taken out of that book to illustrate the idea. So within the parentheses is the probability distribution formula for the Poisson distribution, right? And let's say we have known parameters. Let's say the mean of for Hamilton is 0.31 for each 1,000 words, and the mean for Madison is 0.67 for each 1,000 words. Okay, and using the formula in the parentheses, we can derive, right? We can derive corresponding probabilities for frequencies from 0 to 6. And we can go on to 7, 8, 9, 10, etc. But 6, the probabilities for 6 is small enough, approaching 0. So pretty much we can stop there. Okay? So the first column is the frequency, and the second column corresponds to the probabilities for Hamilton, right? Based on the parameter 0.31. Note that this is the probability for the frequency in a 2,000 word paper, 2,000 word paper. So the parameter actually gonna double, right? And this is the mean for medicine, 0.67 for each 1,000 words. And the third column lists the probabilities for the corresponding frequency. And we can look at the row for the frequency of 4. So for 4 times of also occurring in the 2,000 word paper, the probability for Hamilton is 0.00331, and the probability for medicine is 0.0352. 0352. Okay. And if initially we thought authorship was simply toss up, then the comparison of the probabilities 0.00331 and 0.0352 will give us new odds of about 10 to 1, right? We simply take a ratio of these two probabilities. Okay. So let's continue our Bayesian analysis. Bear this in your mind. The technical details are not that important. Okay? It may take a while. You can pause my video to get into the details and look through my notes. But the thing is that you can follow through my talk conceptually. So let P1 and P2 denote the prior probabilities, the probabilities before the observation. Okay? Basically, prior belief that hypothesis 1 is Hamilton wrote the paper, and hypothesis 2, Madison wrote the paper. So let's say we only have 2 possibilities. We settle on the assumption that the paper was either written by Hamilton or by Madison. Okay, so P1 and P2 denote the probabilities of beliefs that hypothesis 1 or 2 are true, respectively. And let f sub I of x, so here I is equal to 1 or 2, be the conditional probabilities of observing the result x. So here 4 times also in the 2,000 word essay, right? Given that hypothesis I is true. So f sub I 1 of x is the conditional probability of observing the result x, given that hypothesis 1 is true. And then we have f sub I 2 of x, given that hypothesis 2 is true. Then the conditional probability that hypothesis 1 is true, given observation x. Okay, so we reverse the conditional probability, right, of f sub I x, because f sub I x is the conditional probability of observing the result x given hypothesis. But what we're really interested in is the probability of hypothesis, right, given the data that is x, is equal to this ratio. Okay, equal to this ratio. And in the numerator is P1 multiplied by F1 of x. Okay, F1 of x. Okay. Basically, it is a product of 2 probabilities. P1 is the prior belief or prior probability that hypothesis 1, that is Hamilton wrote the paper, is true. Okay, multiply by the conditional probability, okay, of observing, count of 4 out of, in a 2,000 word essay. Given that hypothesis 1 is true, and over P of x. And here I'm not going to get into a lot of details about how to derive this conditional probability. It's because we already studied, supposedly we should have studied that while we look at why we go over Bayes rule and conditional probabilities. Okay? Bayes rule or Bayes theorem and conditional probabilities. Okay. Okay. Now, that conditional probability, that the probability of hypothesis one given X, could lead to this odds. Okay. What is the odds? Because right now I want to know odds of hypothesis, this conditional probability. Hypothesis one is true given X over the probability of hypothesis two is true given X, right? Right. Because we want to know, given observed data X, whether Hamilton wrote the paper versus what? Madison wrote the paper. Okay, and that turns out to be a ratio of P1 multiplied by F1 given X over P2 multiplied by F sub I2 of X. And we can, kind of separate this ratio into two ratios. The final odds actually is equal to, we can reinterpret this equation to be the initial odds, that is P1 over P2, that ratio, multiply this likelihood ratio. The likelihood ratio basically is the ratio of two probabilities, right? Or actually, here is two likelihood, right? Given the hypothesis, what the data look like, right? Hypothesis one and hypothesis two. Okay? And to return to our example, if we thought authorship was a toss-up, this is P1 equal to P2, half and half, then the initial odds will drop out equation, right? Right? So this term gonna drop out because they're equal. Okay? And the final odds is just equal to the likelihood ratio. Okay? And in this case, it is 10 over 1, as calculated previously. Okay? But if we feel strongly that this essay was written by Hamilton or Madison, the initial odds is not equal to 1. Let's say equal to something else. 10 over 1. Basically, that further confirms, the authorship is Hamilton, or 1 over 10. 1/10, then that's kind of reverse of what's presented in the data, right? Then they're going to cancel out. Well, either way, such results either further confirm or discredit such initial belief. So here, it really depends on how we assign our prior beliefs to this initial odds. Our final conclusion can be different.